Hey everyone, welcome back to a new session. This session is session 5. So we're going to be moving into the world of sampling and Bootstrap in this new session. So let me just do a small recap of where we are in terms of the roadmap. So previous couple of sessions, we talked about building models, right? Very simple models, linear regression, logistic regression. Linear regression is the conventional setup. The dependent variable has assumptions, but dependent variables can be pretty much whatever you want. Now it comes to logistic regression, it comes to classification. That's the next step up, right? What happens when you are building models where the dependent variables is categorical? So in that sense, you will need to do logistic regression, right? So been there, done that. We talked about that before. This new session is going to be based upon what we previously been talking about, right? So um, it's also very important session because sampling and Bootstrap kind of set up the groundwork of tree-based model as well as model selection, right? If you want to select different models, well, you need to rerun an experiment. And when you rerun an experiment, you're basically sampling, right? Same goes with tree-based model, right? How do you go above and beyond linearity, right? What constitutes a tree-based model, right? Tree-based model means when you grow trees, you then have to assemble the trees, especially assemble the results come out of each tree, right? In future sessions, we're gonna have to talk about that. But you won't understand that if you don't understand sampling and bootstrap, right? So that's the motivation why sampling and bootstrap is set here. Uh, and another important reason that we want to talk about sampling and bootstrap is based on the setup of how you run a data science problem. You can't just build a model and say, oh yeah, the work is done, right? You have to um, test the model on different subsets, or also known as different fold, right? To make sure that your model is doing exactly what it's supposed to do, right? Previously, we talked about training set, test set, validation set, right? So that by itself is another form of sampling, right? Um, so things like that are something that we have already seen, but this session just put everything together in a nice framework. So that's the motivation. Now here comes the good news. Based on my interaction with students in this class and the feedback form collected from all of you guys, I think most of students already know sampling. So I would imagine this session, the learning curve, it's not as steep as a couple of sessions before. So I think if you completely understood what's happening before, then I don't think there's any problems. So let's go to our repository. This is 2025 fall, right? Remember, that's the correct branch. Going to documents, docs, and then going to this markdown file that says 05 sampling and bootstrap. So of course, you can read it through, and then some students will probably skip the video. That's totally fine. Um, I don't plan on reading this word by word in front of you guys because that would be extremely tedious. I do want to just point out a couple of important um, building block to help you guys set up the foundation on a higher level. So sampling. Sampling means you're selecting subset of data set, right? You're not selecting the entire data set, right? For obvious reasons, sometimes you can't, right? You may or may not obtain the entire population. That's just the nature of, we live in a limited world, right? We have limited resources. Um, and then also because of compute, right? Even if I give you 10,000, 10 million, 10 billion data set, are you just going to run all this through your gradient descent algorithm? Probably not, right? Because that kills the compute. Your computer won't be able to physically conduct the computation. So, based on those reasons, that's why here comes sampling, right? And there are a couple of sampling that you have to know. Just kind of like get on the first name basis, right? Random sampling, well, random sampling means it's random. Random means each data point has equal chance, right? Let's say you have 100 data point, each data point has chance 1 out of 100 to be selected in your sample, right? So that's just random sampling. So typically people say, oh yeah, just shuffle your data. That's kind of like what that means, right? You shuffle your data, everything has one chance, 1 out of n chance, and your sample size of getting selected, right? Um, there's also stratified. Stratified just ensures its proportional representation of subgroups. And I think in today's data science and machine learning, people probably won't use this kind of sampling methods unless you're doing survey and design, right? That's like by itself, technically speaking, another class. You can teach a whole class on survey and design, and there are different ways that you can choose your test results based on different groups, right? Different strata, right? Different strata. So that's what we mean by stratified sampling. Um, Something you have to know, but in reality, if you're doing data science, if you're doing AI, you probably, won't see this again. With a small chance you'll see it. Um, Last thing is systemic sampling. Select data points at regular intervals from the data set. So this is, again, another way of sampling. Again, typically people use approach number one. I personally have not seen a whole lot of two and three going on in today's AI literature. So I'll leave it there. And if you're doing survey and design, you probably come to two and three. But in terms of data science and conventional data science, definitely one is sufficient, right? But you kind of have to know that. And then there's a different comparison of stratified versus cluster sampling. That's what that means, right? Stratify means you already have different subgroups, and then you randomly select one from each subgroup or each strata, right? Um, Clustering means it's completely random, and you just select a random strata, right? So that's kind of like what that means. I think in terms of building neural network algorithm, um, probably not a whole lot of differentiation here and there, unless you're talking about machine learning algorithm, conventional machine learning algorithm, right? Survey and design. Um, Things like, so if you're talking about conventional machine learning algorithm, things like KNN, right? K-nearest neighborhood, you might probably touch upon a couple of these sampling methods. Tree-based methods, right? You might touch upon something like this. Tree-based method, you're probably going to fall into cluster sampling. Towards the right-hand side instead of the left-hand side. Survey and design, you probably want to fall on the left-hand side just because you want to be fair. Um, and then later on in data science, talking about being fair, you probably want to have balanced um, population for each category. You probably want to do a little bit of stratified sampling when you're calculating that F1 score, things like that, right? So point being, a lot of this is empirical, right? We saw a problem and then we're like, oh yeah, use stratified sampling, you can probably kill that bias, right? Or use cluster sampling, you can probably kill that bias. But in terms of just textbook setup, right? Like we're talking about in a class video or in a class lecture, recordings at the places like this, it might be too big of assumption for me as an instructor to say, oh yeah, you should always use stratified sampling, or oh yeah, you should always use cluster sampling. That's probably too big of a conclusion for me to make comfortably, and obviously I won't be making that conclusion. But my experience with this kind of stuff is just know it on a first name basis, know what they're doing, and then when problem happens, this is the tool, right? You need to be aware the tool is there, right? So I think if you can get to that level, I think you're good to go, and I think you're comfortable of conducting a project like that by using these tools at the tip of your finger. So I think that's probably the most important thing. In contrast to sampling, there's also, of course, Bootstrap, right? Bootstrap is a list of steps that's based on sampling, right? Um, so there's really three steps. Random sampling. Random sampling, we talked about that before, right? You have 10 billion population, and then you want to select like 1,000, right? Select like a 3,000, something like that. Um, and you generate multiple data sets, right? For example, here we have a school, but do you measure every single student height from the school? Probably not, right? You just randomly sample 1,000 students, and then this 1,000 students, you can probably measure their heights, right? Um, but what is Bootstrap? Bootstrap is a sample from the experiment population, and then you repeat that, right? You repeat that n times, and whenever you repeat, you're repeating with replacement, right? So let me rephrase that again. What does that mean? So you have a school, you don't measure every single student's body height in that school. If you want to get an average height of the school, right? You select randomly 1,000 students, and then amongst this 1,000 students, you measure five at once, and then the five students are randomly picked from this 1,000 students, right? And then you repeat this process, let's say 100 times. And then you calculate the average of that, right? And that average is going to be asymptotically close or conversion to the population average, right? You can actually prove this, using statistics and statistical inference. If you stats major, you're full-on statistician, you can prove this completely mathematically, and you can get that convergence. So we don't have to go that, but just know that the theory is there, right? The theory is there. That's why this experiment is supported, right? Is supported. So if you do things this way, you can probably finish the experiment in like an hour versus, measuring 1,000 students, it'll probably take 2 hours. That's the ROI that we're talking about, right? In business terminology, that's the ROI we're talking about. And doing things the second way, which is also called bootstrap, it's going to be much more efficient and can also help you get to the right answer. Um, that is kind of it, right? If you just understand what I just talked about, that's kind of it. You pretty much understood what is sampling, what is bootstrap. Um, so the way to go from here is to run an exercise, right? So let me show you guys what's the exercise you can run. Um, Go to win360search.azurewebsites.net, and again, you can talk to any large language model, ChatGPT, Anthropic, whatever, right? So in this case, I'm going to run an experiment. My favorite experiment, it's the pi value, right? The 3.14, the pi value. So the idea is we all know that the pi value is 3.14, right? And then you can probably you kind of get a intuitively think in your head that okay, this is what the circle look like. If I just put a bunch of dots in a circle, it'll probably look like this. You can kind of get an understanding of how that works, right? So I'm gonna describe what I want, and then chatbot will write the code for me, and we can run an experiment, right? So we can say I want to recover the value of pi, which should be 3.14 da 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 da. Um, so I want you to give me a Python code with the following experiment, right? And then you can probably type out what the experiment is, right? For example, first step is create a square, something like that. And the second step is to drop a bunch of dots on the square, right? So drop uh, a bunch of dots on the square. You can think of it as a scatter plot, right? With you can just think about it as maybe just using NumPy random number um, generator. Okay. So you drop a bunch of dots on a unit square. Then what do you do, right? You want to compare if I draw a quarter of a circle, how many dots fall in the circle and how many do not fall in the circle, right? That's the comparison we want to create because the pi value is defined using circle, right? So now that we have a square, now we need to get a circle in there, right? So now, Mark, now create a boundary that is a quarter circle that falls nicely in the square, and mark dots red if they are within the circle, and black if they are not. Okay? Give me a Python function to create this plot, and let me set n sample size of number of dots as input variable, so I can change n and get different simulations. The title should be estimate of pi value based on the number of dots inside of the circle. Parentheses, you'll have to use algebra to reverse engineer the pi value based on the number of dots, right? Dots. Okay, that's the experiment, right? That's what I'm gonna type as a prompt. Now, large language model will give me some Python code, right? That's the idea. So we'll see how this works. Hopefully it works out well. If not, then we'll see what the error is. So while this is loading, I am going to open a Colab, right? Just open any Colab, right? Just search Colab, and then you can get in here and just delete all of it because we don't need all that stuff. Zoom in. This is your Python environment. You can say print hello world, boom, you have your Python. Okay, so now it gave us a couple of code, right? Here's the code. I'll help you create a Python function that estimate pi using Monte Carlo method, which is again sampling by comparing ratio of the points inside of a quarter circle to the total number of points, which should approximate pi over 4. That makes sense, right? And then we just copy this function, nice and easy. Go to our Colab, put a function there, run it, and then here's a couple of examples, right? So examples is estimate pi. Let's start with a smaller number because smaller number, you're probably not gonna get a convergence, right? Smaller number means it's too random, right? It's too random. So let's just say 20. You're probably gonna see something like this, and then the pi estimate is 3.6. Okay, so we got something, right? We got something. We have a bunch of dots, and some of them are inside of a circle. The circle is this blue line, right? It's technically speaking a quarter of a circle. Inside one color, outside another color, right? Now the problem is very simple. You just count the dots, right? If you count the dots, you do the division, it should come out to be pi over 4, right? Why is it pi over 4? Well, it's simple, right? It's because of the radius formula in response to what? In response to the area of a circle, right? The area of a circle is pi r square, right? Or same thing goes with if you use the uh, diameter of a circle, you can reverse engineer the formula of the entire perimeter of the circle, right? Same thing, right? You pick either formula. Either formula works because either formula has pi inside, right? So if you just count the dots, you can reverse engineer with the value of pi. In this case, we reverse engineer the value, and the value is 3.6, and it's not even close to 3.14 because we only have 20 samples, right? So now let's just increase sample. Let's just say, hey, now it becomes 50. Okay, it's 3.36 and it's 50. We see more dots. So number is getting closer to 3.14. Not there yet, but it's closer. And then now you can do 100. You get the idea. Now you have more points. The value gets even closer, 3.28. And then you just keep doing so on and so forth, right? 200. Now the number is going down a little bit. It's closer, but it's going down a little bit. 300, 3.12. Okay, now it's really close, right? Now if I do 500, you get the idea. If I do 1,000, you get the idea, right? If I keep doing 10,000, if I just keep adding circles, eventually it's going to fill up every single location of the circle in and out, right? And then you reverse engineer the ratio, the pi value is going to be very, 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 very close to 3.14, right? And that's the way to understand, okay, what exactly do we mean by sampling? What exactly do we mean by um, the higher level of sampling is Monte Carlo simulation, right? This is how you do a Monte Carlo simulation, which based on sampling. And then if you have no idea what I'm talking about, just ask, right? Let's say you don't know the formula. I think maybe there's oh, the formula is already listed out here. So, that's the formula, right? It's pi over 4, reverse engineer, then you get the value of pi, right? It's 4 times the ratio of the points. Also, that's the formula. We're talking about very simple algebra here. Um, I'm hoping everyone should get this. And I think one other thing I want to say is probably you may ask a question, Monte Carlo simulation. So what's the relationship between Monte Carlo simulation with sampling? You can run the question and it will give you a good enough answer. And then let's see what it says. The Monte Carlo simulation should be based on sampling. It's not exactly the same, but it's based on sampling. And then it's essentially a higher form of sampling. Um, People use all over the places in finance, right? Um, and me personally, whenever I want to get like some sort of distribution of some statistics, right? Let's say average of return of S&P 500, you can probably build some Monte Carlo simulation, get an average, get a standard deviation, you get your distribution that way. It's not correct, right? But it's more correct than how you and I guess what that distribution can be for the return of S&P 500. Um, so let's see. That's my question. What's the relationship between Monte Carlo simulation with sampling? Um, Monte Carlo simulation and sampling are closely related to concepts in statistics and computational methods. Here's a relationship. For relationship, uh, Monte Carlo are essentially sampling methods, right? It's a type of sampling methods. Rely on repeated random sampling, right? Repeated random sampling. Oh, let me tie things up here. I think this is a very important point. So I'm repeating stuff, right? I'm repeating stuff with a different sample size, right? That's basically what I'm doing. Every time I'm repeating the experiment, it's drawing random numbers using a random number generator. In this case, it's a uniform distribution from 0 to 1. That means every single point from 0 to 1, and it can be fraction as well, um, equal chance, right? So that's a uniform distribution. So this falls in the definition of what, right? What we just talked about. So the definition of what we just talked about is equal chance, right? Random sampling, equal chance, right? Equal chance. So alternatively, if you, let's say your keystroke or large language model hallucinate, right? It give you something that is not, technically speaking, uniform. Let's say give you something that's weird, right? With like a tail somewhere on the right-hand side or tail somewhere on the left-hand side. Then for obvious reason, this circle is not going to be a, a flat circle, right? You're gonna see some weird contour somewhere down here, and that's where all the mass is centered. Then in that case, for obvious reason, you're not gonna get a 3.14, right? Does that make sense? So um, to reverse engineer that, let's highlight these 2 lines of code. Let's go to our chat bar. Let's say I want to mess with the distribution a little bit. Um, I want you to change these 2 lines of code. Um, can you give me some strange distribution um, to create X and Y that is not uniform and perhaps has a skew somewhere, right? So if you run this experiment, it will destroy the assumption of random sampling, which means you should be destroying the correct estimate value of pi. Why do we want to destroy it? Well, the reason we want to destroy it is because I want to show you guys what is an incorrect approach, right? So hopefully you guys get the idea. And then this is why we use large language model because out of the box, it gives us 1, 2, 3, 4, 5, 6, 7 different distribution that are all skewed, that will probably contaminate and damage the impurity of this experiment, right? So let's pick one. Let's just pick the first one because it's the easiest one, and let's see how it works. So concentrated in a corner of 0, 0. Okay, so let's copy these 2 lines of code. Let's put it here, right? So I'm going to comment this out, and I'm going to put it here with the correct indentation. I'm going to run this function again, and then I'm going to run this with, let's say 10,000, right? Like 10,000 points on the original function work perfectly fine. We got 3.14, but if you run this, you're not going to get 3.14, right? You're going to get 3.98, even though you have 10,000 samples, right? Well, that's going to be a problem. Why is that a problem? Well, the problem is the center is here. It's not uniform, right? You're creating random numbers with the center that's skewed to one particular location of the square, right? So you've destroyed, what have you destroyed? You have destroyed the assumption that is crucial for random sampling. So once you destroy that, then you destroy your experiment. And once you destroy experiment, your result, for obvious reason, it's not going to work, right? So this way, I just showed you guys, even with 10,000 samples, 3.98, it's not going to work, right? It's not 3.14, right? So this way, hopefully, you guys understand the correct approach, and you guys also understood how to destroy the correct approach, which is what is the wrong approach. And then hopefully in the industry, you have a sharp eye of seeing, okay, someone do things this way, that's wrong, right? It's not wrong in the nature of the real world. It's wrong because who knows, right? Maybe this guy has more insight, right? Maybe this guy says, oh yeah, I want the data to be concentrated that way, right? Fine, then that's their domain knowledge, right? Then that's their domain knowledge. But in terms of just purely consider the fairness of designing an experiment, if you want to use sampling, then use random sample, then everything should be equal chance, right? If not, then obviously, the result is not going to be accurate. So that is pretty much it for sampling and Bootstrap. If you can understand that, kudos to you. If not, I would just recommend to rewatch this video. Um, there isn't really any need for part B, C, D, E, F, G, which previous session I might have went ahead too much. But this is a live session, so if you can understand what I'm talking about in this video, I think you're good to go. Focus on the project. So I think this session overlap with the project a little bit because we extended the deadline, right, from project 1 from last week. So if you still need to work on it, please go ahead and yeah, just let me know if you need extension. Other than that, I think we're good to go. So best of luck with the project, and then I'll see you in the next video.